Section 4.3 introduces us to L'Hopital's rule. Now, L'Hopital's rule helps us when we're finding limits when we end up with indeterminate form. And in section 4.4, when we're going to look at graphing our f of x and also looking for vertical and horizontal asymptotes, it's going to be helpful to kind of remind us at how limits work. Now, just before we get to L'Hopital's rule, let's just remind ourselves a couple of things about limits. The first one, the limit as x approaches 0 of x is equal to 0. This is just direct substitution. The limit as x approaches infinity is equal to infinity. Again, this is direct substitution. The limit as x approaches negative infinity of x is direct substitution. For all of these, we had just direct substitution. Same thing for x squared. The limit as x approaches 0 of x squared is equal to 0. The limit as x approaches infinity of x squared is infinity, because infinity times infinity is positive infinity. And the limit as x approaches negative infinity of x squared, well, a negative infinity times a negative infinity would be a positive infinity. These, recall, is our special limit. The limit as x approaches positive or negative infinity of a number over x to a power is equal to 0. Now let's look at these. For these, recall we used a graph. So if we pull up the graph of these real quick. For the first one, let's look at 1 over x. So in the graph, we're going to hit 1 divided by x, and then graph. Now the limit as x approaches 0 from the right, so those numbers that are bigger than 0, we'll notice the graph is going up, 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 and up, going towards positive infinity. The limit as x approaches 0 from the left, well, from the left, the graph is going down and down and down, so that's going towards negative infinity. And the limit as x approaches 0 of 1 over x, since the limit from the right and the limit from the left did not agree, we said that our limit did not exist. The same for 1 over x squared. Again, let's just put that into our graph real quick. The limit as x approaches 0 from the right, well, 0 from the right, going off towards positive infinity. The limit as x approaches 0 from the left, well, 0 from the left is also going off towards positive infinity. And the limit as x approaches 0, well, this is actually stated on here wrong, would actually equal infinity, because the limit from the left and the limit from the right are infinity, so the limit at 0 is equal to infinity. Now, a couple of new ones that we haven't looked at before were limits involving e to the x and limits involving the natural log of x. So I'm going to draw the graph of both of those real quick. So e to the x has this horizontal asymptote here at y equals 0. It goes through the point 0, 1, and it's up like this. So the limit as x approaches 0 of e to the x, well, this is just direct substitution. E to the 0 is equal to 1. The limit as x approaches infinity of e to the x, well, as you move along to the right, this graph is going up towards positive infinity. The limit as x approaches negative infinity of e to the x, well, as you go towards negative infinity on my x-axis, I'm trying to become y equals 0. So the next ones, take a look at it with e to the negative x, and instead of drawing a separate graph, let's just approach it with the same graph. Again, this is the graph of f of x is equal to e to the x. So the limit as x approaches 0 of e to the negative x, well, e to the negative 0 is just e to the 0, and that's equal to 1, and that's direct substitution. The limit as x approaches infinity of e to the negative x, well, that would be e to the negative infinity, and e to the negative infinity, which brings us this way, means 0. And here the limit as x approaches negative infinity of e to the negative x, well, two negatives make a positive, and e to the positive infinity takes us to positive infinity. Now let's look at the graph of the natural log of x. The graph of the natural log of x has a vertical asymptote here at x equals 0. It goes through the point 1, 0, and it goes up like this. This is the graph of f of x is equal to the natural log of x. So now this says the limit as x approaches 0 from the right, so this is 0 from the right, of the natural log of x, well, you notice it's going to negative infinity. And the limit as x approaches infinity is equal to positive infinity. So these are new ones, and we're going to be using these when we are looking at problems. So now, indeterminate form. Recall from section 2.1 that sometimes when we found the limit of a quotient, we'd end up with 0 over 0, which we said was indeterminate form. So what we would do in section 2.1, if we ended up with indeterminate form, we'd factor and reduce our function and take the limit again. So for example, if we're doing number 1, find the limit as x approaches negative 3 of x squared minus 9 over x plus 3. Well, negative 3 squared minus 9 over negative 3 plus 3, direct substitution leads to 0 over 0, which is our indeterminate form, which means that we could do some algebra here. So what we did in section 2.1 was factor. Well, the numerator is the difference of squares. It factors as x minus 3 over x plus 3 over the denominator of x plus 3, and then we reduced. And then we're looking at the limit as x approaches negative 3 of just x minus 3, and we take the limit again now, and we end up with negative 6. So in section 2.1, whenever we had indeterminate form, again we factored and reduced and then took the limit again. Well, L'Hopital's rule allows us to find the limit of a function that ends up in indeterminate form a different way. So we have the following. If the limit as x approaches c of a function is equal to 0, and the limit as x approaches c of g of x is equal to 0, then the limit as x approaches f of x over g of x, which again would be 0 over 0, is the same as the limit as x approaches c of the derivative of the numerator divided by the derivative of the denominator, provided that the second limit exists or is positive or negative infinity. So instead of factoring and reducing, L'Hopital's rule says, okay, if you want to find the limit and you end up in indeterminate form, all you need to do is take the derivative of the numerator and the derivative of the denominator and then try direct substitution again. So let's go ahead and find the limit as x approaches negative 3 of x squared minus 9 over x plus 3. Well, notice this is the exact same as example 1. So we know that we are going to end up with indeterminate form here because negative 3 squared minus 9 over negative 3 plus 3 yields 0 over 0, which is our indeterminate form. So L'Hopital says, okay, what you can do instead to find this limit is take the derivative of the numerator. Well, the derivative of the numerator is 2x, and then take the derivative of the denominator. Well, the derivative of the denominator, x plus 3, is just 1. And now take the limit of this function again. So direct substitution is 2 times the negative 3 over 1, which is negative 6. Notice it's the exact thing that we found in example 1. So L'Hopital's rule allows us to find the limit if we end up with indeterminate form. So let's look at a couple more examples of this. So let's find the limit as x approaches 0 of 2x over e to the x minus 1. We always start with direct substitution. So 2 times 0 over e to the 0 minus 1 is 0 over 0. So that's again indeterminate form. So now we use L'Hopital's rule. And L'Hopital's rule says, in order to find this limit, first take the derivative of the numerator. What's the derivative of the numerator? Derivative of 2x is 2. And then take the derivative of the denominator. Well, the derivative of e to the x minus 1 is just e to the x. And then take the limit again. So then this is direct substitution 2 over e to the 0 or 2 over 1, which is 2. So the limit as x approaches 0 of 2x over e to the x minus 1 is equal to 2. All right, let's go ahead and do example 4. So first, again, always start with doing direct substitution. So we have 4 minus 4 over 4 squared minus 5 times 4 plus 4. So we're looking at 0 over 16 minus 20 plus 4, which is 0 over 0. So we can use L'Hopital's rule because this is in indeterminate form. So we just take the limit as x approaches 4 of, well, the derivative of the numerator, the derivative of x minus 4 is 1. And the derivative of the denominator, well, the derivative of x squared minus 5x plus 4 is 2x minus 5. And then we take the limit again. Direct substitution yields 1 over 2 times 4 minus 5. so we get 1 over 3. So the limit as x approaches 4 of x minus 4 over x squared minus 5x plus 4 is equal to 1/3. Let's try example 5. Always start with direct substitution. So if we do direct substitution, we get 3 times 0 plus 1 minus e to the 3 times 0 all over 0 squared. So we're looking at 0 plus 1 minus e to the 0 over 0, which is going to be 1 minus 1 over 0 or 0 over 0, which again is our indeterminate form. So L'Hopital's rule tells me that what I can do is take the derivative of my numerator and the derivative of my denominator and then take the limit again. So the derivative of my numerator, well, the derivative of 3x plus 1 minus e to the 3x. So the derivative of 3x is 3. The derivative of 1 is 0. Minus the derivative of e to the 3x is going to be e to the 3x times 3. And the derivative then of the denominator, x squared, is 2x. So let's rewrite this and then take the limit. So we have 3 minus 3 e to the 3x all over 2x. So now let's try direct substitution. So direct substitution, we end up with 3 minus 3 e to the 3 times 0 all over 2 times 0. Well, we end up here with 3 minus 3 all over 0 or 0 over 0, which is indeterminate form. So if you end up with indeterminate form again, you're allowed to use L'Hopital's rule again. So I can use L'Hopital's rule on this. So limit as x approaches 0 of, well, what's the derivative of my numerator? Well, the derivative of 3 minus 3 e to the x is negative 3 e to the 3x times 3 all over the derivative of the denominator, 2x, is 2. So let's rewrite this before we take the limit. And we end up with the limit as x goes to 0 of negative 9 e to the 3x all over 2. Now let's take the limit again. And we end up with negative 9 e times 3 to the 0 all over 2, which is negative 9 over 2. So the limit as x approaches 0 of 3 to the x plus 1 minus e to the 3x all over x squared is actually 9 halves, negative 9 halves. So you can use L'Hopital's rule over and over again if necessary in order to find the limit. So let's do example 6. So again, the first thing you always start with, no matter what, is direct substitution. So here I have 1 plus 1 over 2 minus the natural log of 1, which is 2 over 2 minus 0, which is 1. So this did not need L'Hopital's rule because it wasn't 0 over 0. Direct substitution just ended up giving us that the limit as x approaches 1 of x plus 1 over 2 minus the natural log of x was equal to 1.